Welcome back to the Deep Dive, where we take your curiosity, mash it up with some incredible source material, and give you the knowledge you need, without that crushing weight of information overload.
Today, we are taking a long, hard look at an artifact that, well, it sits at the absolute intersection of faith, history, and cutting-edge science.
We're talking about the Shroud of Turin.
It is, without a doubt, one of the most famous and, most intensely studied pieces of fabric on the planet.
Absolutely. For centuries, this massive, 14-foot 5-inch by 3-foot 7-inch length of linen has been revered as the burial cloth of Jesus of Nazareth.
And it bears this faint, ghostly negative image of a crucified man.
The sources shared by you, the listener, are just phenomenal. They detail the shroud's long, volatile history, its immense religious significance, and the truly exhaustive and often flat-out contradictory scientific analyses.
Oh, completely. We're talking forensics, radiochemistry, botany, even NASA image analysis. It's all been thrown at this thing.
So our mission today is to perform a kind of surgical extraction of the most critical nuggets of knowledge that define this whole debate.
Right. We need to establish the documented timeline and pay close attention to the forgery accusations that, date back almost to its first public appearance.
And then we have to dissect the scientific bombshell of the 1988 radiocarbon dating.
And finally, we have to wrestle with the fascinating but utterly contradictory evidence we get from forensic science about the image itself.
And here's the central paradox, right?
Yeah.
This is what keeps the debate raging, because you have to choose which evidence you prioritize.
Exactly. On one hand, the image looks impossibly real, anatomically detailed, and even three-dimensional, especially when you see it in a black and white photographic negative.
A discovery that wasn't even made until 1898 by the Italian photographer Secondo Pia.
A total accident that changed everything. But then, on the other hand, you have decades of rigorous high-tech testing on the fabric itself.
And that points squarely toward a medieval origin.
Squarely.
So what does it all mean? Okay, let's unpack this.
To start, let's ground ourselves in the physical reality of the cloth. It's a striking object, even without the image. It is rectangular, measuring about 4.4 meters long and 1.1 meters wide.
That's the 14.5 by 3.5 feet you mentioned. I mean, that's far larger than you'd think for a typical burial cloth.
It is, and the material itself, the weave, is a really significant detail, isn't it?
It's not just some plain woven fabric common to the era Jesus lived in, no.
Correct. And this is a crucial technical point that critics of its authenticity often raise. The cloth is woven from flax fibers in a very specific pattern. It's known as a 3-to-1 herringbone twill.
Okay, what does that mean in simple terms?
It's just structurally more complex. It's generally associated with high-quality, more expensive textiles. And some historians argue that this type of, advanced weaving was either very uncommon or maybe even unknown in the first century AD Levant.
So the very fabric it's made of is a kind of historical question mark.
A big one. And this specific weave is the background for that faint, straw-yellow, brownish image that is its key feature.
And that image, it depicts a full-length double impression.
Exactly. It shows the front and back view of a naked man aligned along the body's midplane, with the two head images nearly meeting in the center.
And the man himself.
While forensic and image analysts have described the subject as muscular, bearded, with a mustache and shoulder-length hair parted down the middle.
So pretty consistent with the typical artistic representations of Jesus.
Very consistent.
How tall was the man imprinted on the shroud, based on the dimensions?
The consensus is that he was quite tall for any era, let alone the first century. Analysts estimate his height to range from about 1.70 to 1.88 meters.
Which is roughly 5 feet 7 inches up to 6 feet 2 inches.
A very tall man. And that stature is important when we later discuss some of the anatomical critiques, particularly the length of his arms.
And of course, the other key feature is the reddish-brown stains, which visually correlate with the wounds described in the gospel accounts of crucifixion.
Right, the scourging marks, crown of thorns, nail wounds on the wrists and feet, the spear wound in the side.
But as we'll see later, whether those stains are actually blood is a central, huge scientific dispute.
Oh, it's a massive one. But the visual power is undeniable, and that power just exploded in the modern era with the discovery of the negative image. We have to pause on Secondo Pia's 1898 photograph because that single event just redefined the shroud.
Right. Before 1898, the shroud was this yellowish-brown, kind of indistinct piece of old fabric. It was revered, sure, but the details were muted.
That's right. Pia took the first photograph in Turin, and when he developed the negative, the lights and darks were inverted. What was dim on the cloth became bright on the negative.
And that dim yellow image became a stunningly sharp, positive image of a face.
It was utterly unexpected, a modern sensation. It immediately suggested the image was not a painting in the traditional sense, but some kind of, well, light-sensitive imprint.
It's just astonishing that a medieval object, if it is medieval, would have a property that only modern photography, invented centuries later, could even reveal.
It's the central mystery. The negative effect instantly associated the shroud with the popular Catholic devotion to the Holy Face of Jesus, transforming it from a venerable object into a truly unique icon.
Okay, so let's pivot back to its documented timeline. Because for all the mystery, the history of the cloth itself is surprisingly short and immediately controversial.
That's the thing. The documented history doesn't begin in Jerusalem or Constantinople, but just abruptly, in the mid-14th century, in France.
The first reliable historical record places the shroud in Lire, France, around 1354, exhibited by a knight, Shroud of Turin.
And that is the official starting point for the artifact's paper trail in the West.
And the criticism was swift. We're not talking about skeptics 500 years later.
No. We're talking about people living only a few decades after its first showing.
Which is a massive point against its authenticity.
Precisely. By 1389 or 1390, the controversy had boiled over. Pierre d'Arcis, the Bishop of Troyes, the diocese where Lire was located, he wrote a detailed and scathing memorandum to the sitting anti-Pope Clement VII.
What did he claim? Did he just say it was fake or?
Oh, he gave specifics, stunningly concrete specifics. He explicitly denounced the shroud as a cunning forgery and claimed that a previous bishop, Henri de Poitiers, had investigated and had actually identified the artist who confessed to painting it.
He found the artist who confessed.
That's the claim. The artist's name isn't recorded, but the claim of identifying the perpetrator so early is a devastating historical accusation.
That is the ultimate smoking gun for historians and skeptics.
Yeah.
So how did the papal authority handle that?
Well, the initial papal response was a masterclass in diplomacy. Anti-Pope Clement VII permitted the exhibitions to continue, but he issued an extremely clear, legally binding order.
Which was?
He mandated that at every single public exhibition, it had to be proclaimed aloud that the representation was not the true shroud, but a painting or panel made to represent or imitate the shroud.
So the church basically said, you can venerate it, but you have to keep telling everyone it's an artistic representation, not the real thing.
Exactly. It was a didactic object meant to instruct the faithful, but not a genuine first-class relic. And that early explicit disclaimer is a crucial data point that often gets lost.
So the shroud's history then shifts as it gains powerful patrons, right? That doesn't just stay in this little church.
Not at all. In 1453, it was deeded to the House of Savoy, making it their central protective and revered object. It was moved to Chambéry, France, in the early 16th century.
And that's where it nearly met its end in the famous 1532 fire.
A critical event. A fire broke out in the chapel where the shroud was stored in a silver reliquary chest. Molten silver dripped down, burning holes right through the folded cloth.
Wow.
Fortunately, the image areas themselves were largely spared, but the damage was extensive. Poor Clare nuns immediately did repairs, patching the holes with these white triangular patches you can still see today.
So the patches we see are from that fire.
They are. The shroud was finally moved to Turin in 1578, and it has remained there ever since, housed in the cathedral's chapel of the Holy Shroud.
Given its age and trauma, the modern conservation must be extraordinary.
It's a high-tech fortress. It's stored flat on an aluminum support inside a specialized airtight display case.
Airtight.
Completely laminated with bulletproof glass and filled with an inert atmosphere of argon gas, 99.5% argon with only 0.5% oxygen.
To freeze the chemical processes to stop any more aging? Incredible.
The level of intense scrutiny applied to this artifact is so great that it has its own formal academic discipline, syndenology.
Its own discipline. That's amazing.
Historians, chemists, physicists, forensic pathologists, all dedicated to unlocking the mysteries in this one piece of fabric.
And it all really kicked into high gear after that 1898 photograph.
Yeah.
But all of it, for better or worse, has to contend with the single most famous scientific finding.
The 1988 radiocarbon dating.
The bombshell.
That was the moment the scientific world weighed in decisively. After years of negotiation, permission was finally granted to perform the test.
So explain the logistics. How was the sample taken, and what did they do to make sure it was impartial?
A small swatch of linen was taken from a non-image area near a corner. This sample was then divided and sent to 3 independent, internationally respected labs.
Oxford, Arizona, and Durham.
The Swiss Federal Institute of Technology in Zurich. And they performed blind testing. They didn't know what they were testing, just that it was ancient fabric.
And the conclusion was pretty clear.
It was. With 95% confidence, the three labs collectively concluded that the linen material dated to a period between AD 1260 and 1390.
And that time frame, I mean, that's just a perfect match for its first documented public appearance in France, right?
A perfect match. It aligned perfectly with the first exhibition and the 14th century forgery accusations we just discussed.
So for most mainstream scientists, that was it. Case closed. It's a magnificent but medieval artifact.
From a radiochemist's perspective, yes. But for the proponents of authenticity, the syndenologists, the date just deepened the paradox. They immediately began mounting arguments to challenge the date.
Okay, let's unpack those challenges. The most famous one is the medieval repair hypothesis.
Right. This hinges on the location of the sample. It was from a corner near a damaged edge. The theory suggests the sample was taken not from the original first-century material, but from a fragment of thread woven in during a medieval repair process.
Like an invisible mending job.
Exactly. But subsequent analysis of the thread structure showed that the weave of the sample was generally consistent with the main body of the shroud. It didn't really hold up to scrutiny.
But what about other kinds of contamination? The biocontamination theories. This thing is old, it's been handled, it's been in a fire.
Absolutely. The argument is that centuries of exposure to bacteria, fungi, soot from the fire, all of that deposited new, younger carbon onto the fibers, making the whole thing seem younger than it is.
Could that really shift the date by over 1,000 years?
It's highly debated. The labs use rigorous cleaning protocols to remove contaminants. The counterargument is that the unique properties of the shroud, maybe the fire, might have sealed some contaminants inside the fibers where the cleaning couldn't reach them.
So the argument isn't that C14 dating is wrong, but that the sample wasn't clean.
That's the crux of it. And then there are researchers who just went back and looked at the raw numbers from 1988. This is the statistical inhomogeneity argument.
Okay, deep dive into the data itself.
Exactly. A 2020 analysis suggested that the data from the three labs lacked perfect homogeneity, a statistical term meaning the results weren't quite consistent enough to guarantee they all tested identical samples.
Meaning something was maybe different about one of the samples.
It implies something unusual was happening at the molecular level in at least one swatch. Maybe subtle contamination or an abnormality in the weave. The study suggested that if you adjusted the results by just 88 years, they would all fall into perfect statistical agreement.
But the original results didn't need any adjustment to land firmly in the medieval period.
Correct. The consensus is still strong, but it's these statistical fine prints that keep the skepticism alive. It's the perfect paradox. Clear answer, but maybe, just maybe, some unclear certainty.
So if the radiocarbon dating were the only piece of evidence, this would all be over. But it's not. The physical properties of the image itself, this is what defies easy explanation.
This is what elevates the artifact. We have to start with the superficiality of the image. It's not paint. It's a chemical change to the cellulose structure of the flax fibers themselves.
A translucent and discontinuous yellow discoloration.
And the depth of that chemical change is the crucial technical nugget.
This is the part I can't wrap my head around.
It's the single most baffling feature. The discoloration affects only the top 2 or 3 fibers of the threads, and it penetrates only about 200 nanometers into the external cell layer of each fiber.
Okay, 200 nanometers. To put that into scale for me, how small is that?
Well, a typical human hair is about 80,000 to 100,000 nanometers.
Oh, wow.
So we're talking about 1,500th of the diameter of a human hair. It is shallower than the resolution of the human eye.
So if a medieval painter had used a brush, the pigment would have soaked in much deeper.
Oh, absolutely. It would have created capillary action along the fibers. We don't see that here. And furthermore, the image isn't formed like a photograph where you vary the intensity of the color. It's an areal density image.
A halftone image.
Yeah.
Like a newspaper photo.
Exactly. The darkness depends on the number of yellowed fibers per unit area. In dark areas, almost every fiber is discolored. In light areas, only a few are. It suggests the process was highly controlled and extremely localized.
Which brings us to the famous 3D quality. This is the one that always gets cited as proof it's not a forgery.
It's compelling. In 1976, researchers used NASA technology, a VP8 image analyzer, on photographs of the shroud.
What did they find?
Something extraordinary. The image intensity was inversely related to the estimated cloth-to-body distance.
Meaning the parts of the cloth that would have been closer to the body, the nose, The forehead are the faintest, and the areas farther away, like the eye sockets, are the darkest.
Yes, the shroud literally encoded three-dimensional information. When you process it through a computer, it resolves into a remarkably realistic three-dimensional sculpture.
But there's a catch, right? It's not perfect.
It's not. The mapping isn't perfectly consistent with direct contact in all areas. And critics argue you could replicate this effect with, say, a bas-relief sculpture and specific lighting or chemical fogs.
Okay, so now let's move from the body image to the reddish stains. The question is it blood?
And this is where the experts truly came to blows. In 1978, the Shroud of Turin Research Project, or STURP, got unprecedented access. But at the same time, a microscopist named Walter Macrone took his own samples.
And Macron was a big deal in forensics.
A very big deal. And his conclusion was unequivocal. He said the body image was made with red ochre pigment in a gelatin medium. And the bloodstains.
What about them?
He found they were highlighted with vermilion, which is mercury sulfide pigment, also in gelatin.
Wait, mercury sulfide? That's just paint.
According to Macron, yes. He stated explicitly that he found no actual blood. He said the shroud was a masterful painting.
But the main STURP team?
Mm-hmm.
They vehemently disagreed.
They did. They used different methods, like spectroscopy, and they agreed there was iron oxide, but they argued it wasn't the source of the image. They rejected his conclusions completely.
So you have two respected groups using different scientific methods, coming to completely opposite conclusions.
It's the core of the conflict. It actually led Macron to resign from STURP.
And more recently, we got DNA analysis in 2015. What did that add?
Oh, just more complexity. They found human DNA from incredibly diverse groups: Europe, North Africa, the Middle East, even India.
So what does that mean?
It could mean anything. It's compatible with the shroud having traveled from the Near East. But they also found plant DNA and genetic markers that raise the possibility of an Indian manufacture of the linen cloth itself.
So the cloth might be from India.
It's a possibility the DNA raises. But to circle back, despite all this, has it ever been definitively proven that the stains are human blood?
I'm guessing no.
No, it has not been scientifically demonstrated, which leaves Macron's pigment finding just hovering over the debate.
And finally, on the forensic side, there are the anatomical flaws.
Yes. Early on, proponents claimed it was flawless. But later studies found significant contradictions.
Like what?
The arms appear far too long. The right arm is especially elongated, and the right hand is disproportionate.
And that elongation serves a very specific purpose.
It does. It allows the hands to cross over the genital area, covering the nudity in a way that's actually anatomically unrealistic for a relaxed corpse. It seems more like an artistic choice, reflecting the modesty of the 14th century.
And then there's the modern bloodstain pattern analysis.
A 2018 study concluded the blood flows are highly inconsistent. The rivulets on the forearms and the hand aren't connected. They would have required a sequence of impossible movements.
So the body would have had to be moving around after being wounded.
Exactly. The patterns are inconsistent between the front and the back of the body. The conclusion was that the blood was likely applied by an artist with a didactic intent to tell the story of the suffering.
This is where the mystery just reaches its peak. We have this solid C14 date, placing it in the Middle Ages. And yet we have these forensic properties that seem impossible for that era. So if it's medieval, how on earth did they do it?
That is the great challenge. How do you reverse engineer a plausible medieval mechanism for this?
Macron's idea was just simple painting, right? Grisaille?
Yes, using red ochre in a gelatin binder. His theory for the faintness was just simple wear and tear. Over centuries of handling, the pigment slowly rubbed off, leaving only the faintest trace.
But that struggles with the 3D property. That's where the bas-relief rubbing technique comes in.
An idea from Joe Nickell. It's compelling because it directly addresses the 3D problem. If you wrap a cloth around a full statue, you get wraparound distortion. The image looks stretched.
But the shroud doesn't have that.
No. So Nickell proposed they used a low-relief sculpture. You drape the cloth over it so it's mostly flat, and then you apply pigment with a rubbing technique, like from a gravestone.
And that would naturally create the 3D encoding.
It would. And researchers have replicated this. One used wet linen over a bas-relief and dabbed it with a mixture of ferric oxide and gelatin. The resulting image was wash-resistant and could withstand high heat.
So that's a plausible medieval mechanism?
It's a strong candidate. It solves the geometry and durability questions. It suggests ingenuity, not an unknown quantum event.
Then there was Luigi Garlacelli's attempt in 2009, the acid pigmentation method.
He tried to replicate the chemical nature of the discoloration. He rubbed linen over a volunteer with an acidic pigment and then aged it with heat and washing.
How did that turn out?
Visibly similar, but critics said it lacked the original's uniformity and fine detail. So we have plausible mechanisms, but the true method, it remains elusive.
We should briefly mention the non-scientific theory, the one you always hear, that it was a burst of radiation at the resurrection.
The fringe theory, it's overwhelmingly rejected by physicists.
Yeah.
A corona discharge or something similar would leave signatures like charring or fusion in the linen that just aren't there.
But the underlying idea that energy caused the discoloration isn't totally dismissed.
That's the nuance. Scientists agree that high-intensity UV light could create this specific type of discoloration. The challenge is, how could a medieval artisan apply UV light with such perfect geometric precision? The paradox persists.
To really understand the Shroud, we have to put it back into its religious context. The Gospels themselves complicate the claim.
They do. Matthew, Mark, and Luke mention a single shroud or synonym. That fits.
But John's Gospel.
John's Gospel, which claims to be an eyewitness account, is different. He mentions linen cloths, plural, and says the cloth for the head was rolled up in a separate place.
That's a huge inconsistency. The Shroud of Turin is one single piece of cloth.
Exactly. And this was noticed centuries ago. John Calvin used this discrepancy in 1543 to argue against its authenticity. So even before science, there was theological criticism.
Despite all this, the Catholic Church has maintained this, well, remarkably consistent, nuanced position.
Extremely careful. It's a position of reverent neutrality. The Church neither formally endorses nor rejects its authenticity.
Pope Francis called it an icon of a man scourged and crucified.
That phrasing is intentional. It focuses on its spiritual power as a mirror of the gospel, not its factual origin. Pope John Paul II was even more explicit. He said authenticity is not a matter of faith and entrusted the investigation to scientists.
So as we bring this deep dive to a close, what is the final contradictory status of this artifact?
We have an artifact with a documented medieval history and a radiocarbon date from 1260 to 1390. That's accepted by the vast majority of scientists.
And it fits the forgery accusations perfectly.
Perfectly. Yet, the physical characteristics of the image, its incredible 200 nanometer superficiality, its halftone quality, its 3D encoding, remain scientifically baffling and difficult, if not impossible, to replicate perfectly.
The Shroud of Turin is perhaps the ultimate Rorschach test. You have to choose which evidence is more compelling, the dating of the material or the physics of the image.
And that choice often determines whether you approach it with faith, believing the image is a miracle, or with pure empiricism, believing the date is proof and the image is just a mystery we haven't solved yet.
The Shroud is the perfect artifact of information overload, a convergence of faith, forensics, chemistry, and history, where every clear answer just spawns a new, more complex question.
It's a remarkable piece of linen. We noted the DNA analysis showed it contains traces suggesting it traveled through or was exposed to people from the Near East, North Africa, Europe, and maybe even India.
And its status as a venerated object was cemented early. Pope Julius II authorized its veneration as a true relic way back in 1506.
That historical power is immense. The debate over how it was made is vital, but maybe its true significance lies not in who made it, but in the power it held and still holds over people and beliefs across continents.
This relic drove pilgrimages, war, intense scientific scrutiny for 6 centuries, regardless of its C14 date. That legacy, the human response it generated, is undeniable.
Something for you to mull or explore on your own.
A powerful reflection. Thank you for joining us for the deep dive. We'll see you next time. Welcome back to the Deep Dive, where we take some of the most advanced, really mind-bending concepts in modern physics and try to distill them into something we can all understand.
And today we have a big one.
We really do. Today, we are wrestling with a concept that fundamentally challenges, well, everything you think you know about physical reality. The holographic principle.
It is, without a doubt, one of the wildest ideas to come out of theoretical physics. It suggests that the three-dimensional space we inhabit, our entire universe, might not be as real as we perceive it.
Right. So our mission for this deep dive is to unpack that, to really get our heads around this radical idea.
We need to trace it from the beginning. It has these really surprising origins in, of all places, black hole physics.
And from there, we'll follow it through the information revolution in physics, see how it became this incredibly powerful mathematical tool.
And finally, we'll look at where researchers are today. I mean, are they actually trying to test if our reality is some kind of cosmic illusion?
Okay, so this isn't just an analogy, like a fun little thought experiment.
Not at all. The holographic principle is it's a supposed property of quantum gravity. It's a core feature of string theories.
And at its heart, it says what? That a 3D volume of space
Can be fully, and I mean completely, encoded on its boundary. A lower dimensional surface, like a 2D gravitational horizon. It's like gravity itself demands this incredible economy of information.
There's a quote that always comes up here, the one from Leonard Susskind, that just perfectly captures how audacious this is.
Oh, I know the one.
He said, "The three-dimensional world of ordinary experience is a hologram, an image of reality coded on a distant two-dimensional surface."
Right.
So when he says that, is he just saying that, depth is just something our brains invent?
Right.
Or is it literally, mathematically not fundamental?
He's implying the latter. Absolutely. At the most fundamental level, the degrees of freedom, the bits of information you need to describe the universe, they don't scale with volume, they scale with area.
So the third dimension, depth.
It's an emergent illusion. It's a really effective one, but it's not primary. It's how our minds process this incredibly dense information that's actually living on a 2D boundary.
That is a serious claim. And it didn't just appear out of nowhere. It came from people like Gerard Hooft back in '93, right?
That's right. Verhooft really laid the groundwork. He saw it as a necessary requirement for any workable theory of quantum gravity. And then Susskind came along and gave it its very precise string theoretic meaning.
Building on even earlier work.
Exactly. Synthesizing Hooft's ideas with some really technical observations from Charles Thorne way back in 1978. So this has been brewing for decades.
So for you, listening to this, the reason this matters is that it completely redefines the basic building blocks of the cosmos. If this principle holds, then matter and energy, they're not the main show.
They become incidentals. That's the word Jacob Bekenstein used. They are incidentals to information. This was a huge shift, heavily influenced by John Archibald Wheeler.
Wheeler's famous it from bit.
It from bit. The physical world, the it, derives its entire existence from information, the bit. So if the universe is a hologram, its true reality isn't in its shape or its contents, but in the pattern of information written on its boundary.
Okay, let's start digging into that rabbit hole. Where did this all begin? This idea of encoding a 3D volume on a 2D surface. It must have come from somewhere concrete.
It did. It came directly from trying to figure out what happens to information when it gets near a black hole.
So, black hole thermodynamics.
Exactly that, and a concept called the Bekenstein bound. This was the unexpected spark that lit the whole fire.
Okay, set the stage for us. Before all this, what was the standard assumption in physics about information and space?
Well, normally, in classical physics, even in basic statistical mechanics, if you want to know the maximum information capacity of a region, what we call its entropy or disorder, it scales with the region's volume.
Which makes intuitive sense. Radius cubed. If I double the size of a box, I can fit way more stuff, way more information inside.
8 times more, right. That's the volume law. It's what we expect from living in a 3D world.
But Bekenstein found something different.
Something totally different, and it was all because of black holes. He made this incredible conjecture that the maximum entropy in any region of space, the Bekenstein bound, doesn't scale with volume. It scales with the radius squared.
The area.
The area. It's an area law, and that was just a radical departure. It means the information content of a system isn't limited by how big it is on the inside, but by the size of the surface that contains it.
So wait, if I have a giant warehouse, the amount of stuff I can store isn't determined by the cubic footage inside, but just by the square footage of the walls.
That's the analogy. It's deeply counterintuitive. And the place where you see this law in action most clearly is a black hole.
How so?
Bekenstein realized that all the information of everything that has ever fallen into a black hole, stars, gas, planets, all of it, is somehow contained or encoded in the surface fluctuations of its event horizon.
And the event horizon is a two-dimensional boundary.
Fundamentally, yes. A 2D surface holding all the 3D information.
Okay, and this insight wasn't just a clever idea. It was a necessary fix for a huge, catastrophic problem in physics.
A huge one.
Because originally black holes were thought to have zero entropy, right?
That's right. In Einstein's theory of general relativity, they're perfect, simple objects. They're described by just three numbers: mass, charge, and spin. No internal randomness, no complexity, so zero entropy.
And that puts you on a collision course with the second law of thermodynamics.
The most reliable law in all of physics, yeah. The law that says entropy or disorder in a closed system must always increase.
So you take a hot cloud of gas, something with very high entropy, and you throw it into a black hole.
Poof! Once it crosses the event horizon, all that information, all that randomness just vanishes from our universe. The black hole settles down and its three numbers change a little, but that's it. If the black hole itself has zero entropy, then the total entropy of the universe has just gone down.
Which can't happen.
Which can't happen. It would shatter the second law.
So the only way out is to say that black holes aren't simple objects at all. They must be incredibly random. They have to have entropy.
And that entropy has to increase by an amount that's at least as much as the entropy of the gas you threw in. This is where the big theoretical debates really started.
Bekenstein proposed this, but Stephen Hawking was against it at first, wasn't he?
Very much so. Hawking had actually proved something called the area theorem, which states that the total surface area of a collection of black holes can never decrease. He even called it the second law of black hole thermodynamics.
But he thought it was just an analogy.
He did. He resisted the idea of it being real entropy, because if a black hole has entropy, it must have a temperature. And if it has a temperature, it has to radiate energy.
And nothing escapes a black hole.
Classically, no. So he argued they must have zero temperature and therefore zero entropy. He thought Bekenstein had it wrong.
But then, his own calculations, bringing quantum mechanics into the picture, forced him to change his mind.
Completely. He did a careful analysis of quantum fields near an event horizon and made his most famous discovery. Black holes do radiate.
Hawking radiation.
Hawking radiation, this slow thermal leakage of energy. So if they radiate, they must have a temperature. And if they have a temperature, they must have an entropy. Bekenstein was right all along.
And Hawking then came up with the precise formula, didn't he? The one that connects gravity, quantum mechanics, and thermodynamics.
He did. He fixed the exact number, the constant of proportionality. Black hole entropy is precisely 1/4 of its horizon area, measured in Planck units.
The Hawking-Bekenstein formula.
That's the one. It's this beautiful, profound connection. The number of microstates, which is really the total information content, is proportional to the area, A, not the volume inside.
Let's talk about those Planck units for a second. When you say A divided by 4 in Planck units, what does that actually tell us?
It tells us about the granularity of reality itself. The Planck length is the tiniest meaningful unit of distance, about 10 to the minus 35 meters. When you measure the horizon's area in those tiny little squares, it turns out that every 4 Planck squares can hold exactly 1 bit of information.
So the event horizon is like the universe's ultimate hard drive with a fixed information density.
Yeah, perfect analogy. And that area law is the absolute foundation of the holographic principle.
But this isn't a completely settled issue. I mean, you mentioned these things called Wheeler's bags of gold.
Right. It's important to mention the caveats. These are theoretical solutions in classical general relativity. They are configurations where you could, in theory, pack more entropy into a region than its surface area should allow.
So they would violate the Bekenstein bound.
If they could exist, yes.
So why don't they break the whole theory?
Well, the consensus among physicists is that these are artifacts of the classical theory. The belief is that a full theory of quantum gravity, the very theory where the holographic principle must operate, would simply forbid these solutions. They'd be unstable or impossible to form.
So their existence in the classical theory actually reinforces that the area law is a feature of quantum space-time.
Precisely. The holographic principle acts as a kind of filter. Any successful theory of quantum gravity must naturally get rid of things like bags of gold. It's a key requirement.
Okay, so we've established the black hole surface as this amazing information storage device. Now let's make the leap from a single black hole to the entire universe.
This is the big pivot. If we take this area law seriously, it forces a massive shift in our worldview. We have to stop thinking of the universe as being made of stuff, matter, and energy, and start seeing it as being made of information.
And you mentioned this is where Bekenstein was really pushing things, connecting physics to, well, to computer science almost.
He was. He keyed in on this incredible, unexpected connection between two different definitions of entropy.
A tale of two entropies.
A tale of two entropies. First, you have thermodynamic entropy. From Ludwig Boltzmann in 1877, this is what physicists use to measure disorder. Really, it's a count of all the possible microscopic states the particles in a system could be in.
So for a box of gas, it's the number of ways you could arrange all those atoms.
Exactly, a measure of complexity. Then, almost a century later, you get Shannon entropy.
From Claude Shannon, the father of information theory.
Right, and this has nothing to do with hot gas. This is about data. It's an objective measure of the information content of a message, measured in bits. It's what's used in your phone, on your hard drive, everywhere.
And what's so amazing is that these two ideas, born in completely different fields, turned out to have the same mathematical form.
Identical. Shannon's formula for the uncertainty in a message looked just like Boltzmann's formula for the disorder in gas. And Bekenstein said, this is not a coincidence. They are conceptually equivalent.
So the number of ways you can arrange particles, Boltzmann's entropy, is directly related to the amount of information in bits you'd need to describe that arrangement.
That's it. The only real difference is the units. One is in energy per temperature, the other is in dimensionless bits, but they're measuring the same fundamental thing, complexity.
And once you establish that equivalence, information and physical reality become deeply intertwined.
They become the same thing. Information becomes the most fundamental ingredient. Matter and energy are just how that information is manifested to us.
Which means the holographic principle becomes a universal statement. We take what we learn from black holes.
And we generalize it. We say the entropy of any region of space, not just a black hole, is ultimately limited by its surface area, not its volume.
Which leads to the unavoidable conclusion that volume itself, the 3D space we move through, is somehow an illusion.
It's an emergent phenomenon, a projection. The correct term is that the universe is isomorphic to the information on its boundary.
Isomorphic, meaning a perfect one-to-one mapping.
Yes. Every single thing that can happen inside the 3D volume is perfectly and completely described by the physics happening on that 2D surface. The depth we experience is just a consequence of how that boundary information is organized.
It's like the universe is a book, and we're experiencing the story, but the fundamental reality is just the ink on the page.
A great way to put it. And that page, that boundary, isn't some wall you can fly to. It could be the boundary of the universe at infinity. The point is, the complexity, the degrees of freedom grows with area, not volume.
Okay. A claim as huge as volume is an illusion needs some serious mathematical backup. We can't just leave it as a concept. Is there a working model where this actually happens?
There is, and it's the most rigorous, most successful realization of the principle we have. It's called the ADI-CFT correspondence.
The anti-de Sitter conformal field theory correspondence, also known as the Maldacena duality.
That's the one. It is the concrete mathematical proof that, yes, a theory with gravity in a higher dimensional volume can be exactly equivalent to a quantum theory without gravity living on the boundary of that volume.
Let's break that down, the two sides of it. First, the bulk side. Anti-de Sitter space, or ADS. What is that?
ADS is a specific kind of space-time geometry. The key thing is that it has a negative cosmological constant.
Unlike our universe, which seems to have a small positive one.
Right. Our universe is expanding and accelerating. ADS space sort of curves back on itself, and, crucially, it has a boundary at infinity. That boundary is absolutely essential because that's where the other side of the duality, the CFT, lives.
So the ADS space is the higher dimensional volume that contains gravity and string theory.
Yes, that's the bulk.
And on its boundary lives the CFT, conformal field theory. What's a CFT?
A conformal field theory is a type of quantum field theory that has a special kind of symmetry. It looks the same at all scales. If you zoom in or zoom out, the physics doesn't change.
And these are theories we understand pretty well.
Very well. They're like the Yang-Mills theories that describe the elementary particles in the Standard Model. They describe physics without gravity.
So the duality, the correspondence, says that these two completely different-looking universes, one with gravity and strings in, say, 5 dimensions, and one with just quantum particle physics in 4 dimensions,
are mathematically identical. They are two different languages describing the exact same physical reality.
What makes this so incredibly powerful for physicists?
It's what we call a strong-weak duality. And this is the magic trick.
Okay.
In physics, things get really, really hard to calculate when forces are strong. Think of the strong nuclear force that holds quarks together inside a proton. The math just breaks down.
Right, you can't just make small corrections. The interactions are too chaotic.
Exactly. It's mathematically intractable. But here's the amazing part of ADS-CFT. When the physics on the boundary CFT side is strongly interacting and impossible to solve,
Uh-huh.
the physics on the gravity ADS side becomes weakly interacting and simple to solve. You can use the classical equations of general relativity, basically.
Wait, so you're telling me you can take an impossible problem in quantum physics, translate it into a simple gravity problem in a higher dimension, solve it there, and then translate the answer back?
That is exactly what it is. It's like a universal mathematical cheat code.
Give me an example.
The quark-gluon plasma. This is the stuff that filled the universe for the first few microseconds after the Big Bang. It's a soup of quarks and gluons, and it's incredibly strongly interacting.
Impossible to calculate its properties from first principles.
Almost. But using ADS-CFT, physicists translated that problem. The strongly coupled plasma became equivalent to a simple, classical black hole living in the 5D ADS bulk.
A black hole represents the quark-gluon plasma.
It does, and they could easily calculate the properties of that black hole, like how it absorbs energy. This gave them a prediction for the viscosity of the plasma, how easily it flows.
And what happened when they did the experiment? At places like the relativistic heavy ion collider.
The results were a stunning confirmation. They created the quark-gluon plasma, and it behaved like a near-perfect fluid with incredibly low viscosity, a value that matched the prediction from the black hole calculation almost perfectly.
Wow. So it actually works. It makes real-world, testable predictions.
It does, which is why Maldaceno's 1997 paper on this became the most cited paper in the history of high-energy physics. It gave physicists a brand new, powerful toolkit.
And this idea wasn't entirely new, was it? Brown and Eno had a precursor to this.
They did. Back in 1986, they showed that gravity in a 2+1-dimensional ADS space was equivalent to a 2-dimensional CFT. So they proved the concept was possible long before the full correspondence was worked out.
Okay, so we have the theory, we have the mathematical model. Let's circle back to the problem that started it all. The black hole information paradox.
Right.
How does the holographic principle actually solve it? What happens to the information?
So the paradox, just to recap, was that Hawking's original calculation suggested that the information of whatever falls into a black hole is permanently destroyed when the black hole evaporates.
A violation of quantum mechanics.
A huge one. Quantum mechanics says information can never be truly lost. So for decades, physicists were stuck.
And Susskind, using holography, came up with the answer.
He did. He argued that the information isn't lost because it never truly makes it inside in the way we think. The infalling matter leaves an imprint, an engraving of its information, on the furiously vibrating 2D event horizon.
So the horizon isn't a passive boundary. It's a scrambling device.
A quantum scrambling device. It takes the information, scrambles it completely, and then slowly re-emits it as subtle correlations within the outgoing Hawking radiation.
So the information gets out, it's just incredibly hard to decode.
Exactly. The total quantum state is preserved, information is safe, and the holographic resolution is that the 3D interior we imagine is just an effective description. The real physics, the fundamental degrees of freedom, are on that 2D horizon.
And this idea that information has a maximum density, the Wittgenstein bound, it has other huge implications, doesn't it, for the very structure of matter?
It does. If any finite volume can only hold a finite amount of information, that puts a hard limit on how complex things can be.
So in classical physics, you could just keep dividing matter up forever.
Yeah.
A particle could have infinite internal parts.
Infinitely. But if that were true, a single particle could contain an infinite amount of information. And if you put it in a box, you would immediately violate the Wittgenstein bound. The box would collapse into a black hole.
So the holographic principle basically says that you can't divide matter forever. The subdivision has to stop somewhere.
It has to. It implies that reality is fundamentally granular. It has a minimum resolution. It has pixels, so to speak, at the Planck scale.
A pixelated universe.
Yeah.
That's a testable idea, isn't it? Has anyone actually tried to look for this cosmic pixelation?
Yes, there have been attempts. The most famous was probably by a physicist at Fermilab named Craig Hogan.
What was his idea?
He argued that if space-time is fundamentally pixelated or granular, it should lead to a kind of intrinsic jitteriness, a holographic noise, tiny random quantum fluctuations in the very position of things.
And he thought he could measure this.
He built an experiment called the holometer, a very sensitive interferometer, specifically designed to look for this tiny correlated spatial fuzziness.
Did he find it?
He did not. The holometer didn't detect the noise he predicted. And to be fair, his specific predictions were controversial. Most string theorists argue that if this noise exists, it would be far, far smaller than what his experiment could detect.
And wasn't there an astronomical observation that also contradicted it?
There was, and it was a pretty strong blow. In 2011, scientists analyzed the light from a very distant gamma ray burst. The sharpness of the signal allowed them to put a very strict limit on any fuzziness of space-time. They found that space was smoothed down to a scale of 10 to the minus 48 meters, which is vastly smaller than the scale Hogan was predicting. So that specific model of holographic noise seems to have been ruled out.
So where does the research go from here? If ADS-CFT is the gold standard, but our universe isn't ADS space.
That's the frontier. The cutting edge of research is trying to move beyond ADS space. This has led to a new subfield called celestial holography.
Trying to build a hologram for our actual universe.
That's the goal. Our universe is what we call asymptotically flat. It's not closed like ADS. So researchers like Andrew Strominger at Harvard are trying to figure out how to formulate a holographic duality for our kind of space-time.
And where would the lower dimensional hologram live in this case?
The idea is that it lives on the celestial sphere. This is a mathematical sphere at the infinite future boundary of our space-time, where light rays end their journey.
So the entire history of our 4D universe could be encoded on a 2D sphere in the far, far future.
That's the conjecture, and they're trying to make this testable. The idea is that the underlying symmetries of this 2D celestial theory should leave imprints on things we can observe today.
Like what?
Specifically in the patterns of very low-energy particles, like soft gravitons and soft photons. The dream is that we might one day be able to see the signatures of the celestial hologram in the fine details of gravitational waves detected by observatories like LIGO or LISA.
So this is moving from pure theory to something that could one day be observational science.
That's the hope. It's an attempt to take the profound lessons we learned from black holes and apply them to the entire cosmos we live in.
What a journey. I mean, we started with this strange little puzzle about black holes.
That their information content was written on their surface, not stored in their volume.
And that one idea, that area law, snowballed into the holographic principle, which suggests that the third dimension itself might be an emergent illusion.
We then saw how this was given a rock-solid mathematical foundation with the ADS-CFT correspondence, this incredible tool that lets us solve some of the hardest problems in physics.
And now, the quest is on, with things like celestial holography, to see if we can actually prove that our universe, the 4 dimensions we experience, is just a projection of information written on a boundary we can't even see.
You know, if you really take a step back, the biggest takeaway from the holographic principle is that the universe isn't defined by its physical contents. It's not about the matter or the energy. It's about the information it contains, the bit that creates the it.
Which leaves a pretty profound final thought.
It does. If the volume is illusory and all the information is really encoded on some distant boundary, then what is the true nature of that boundary? Is it just a mathematical convenience? Or is that boundary where the fundamental, irreducible reality of our universe actually resides?
Something to think about the next time you look up at the night sky. Thank you for taking this deep dive with us. We'll see you next time.
If I asked you to plan a road trip across 2 continents, say, starting in the UK and ending thousands of kilometers away in Siberia, you'd probably start by looking up the most robust, high-clearance, 4-wheel drive vehicle you could find, right? Something reliable, maybe a brand new professionally supported rally car.
That would be the logical choice. Of course. But logic is precisely what the Mongol Rally was designed to oppose. We are here today to explore a phenomenon that celebrates mechanical failure and, well, logistical chaos.
Right.
This is an intercontinental journey spanning roughly, 13 to 16,000 kilometers.
That's just a staggering distance.
It's equivalent to traversing North America end to end, twice. And the whole point is that you have to do it in a car you wouldn't trust to drive across your hometown.
Exactly. This is the ultimate test of human endurance married to automotive incompetence. You start in Western Europe, the UK, the Czech Republic, or perhaps points further south like Italy or Spain. And the original goal was Ulaanbaatar, Mongolia. But as we'll unpack, even the finish line had to be moved, a direct result of bureaucracy battling idealism.
Yeah, the rally now culminates in Ulan-Ude, Russia.
Yeah.
And this geographical shift isn't random. It's a testament to the persistent struggle between The rally's, let's say, anarchic spirit, and the cold, hard realities of international trade law.
But the distance is still staggering.
Oh, the distance remains staggering, the terrain is unforgiving, and the singular, simple objective for you, the participant, is to try and make it to the finish, knowing your vehicle is intentionally ill-suited for the task.
So our mission for this deep dive is to really unpack the core identity of the Mongol Rally. We need to go beyond the surface-level idea and understand the three fundamental, almost absurd rules that define this high-risk, unsupported adventure. And crucially, we're going to trace how external pressures, namely overwhelming popularity and rigid government bureaucracy, force this event to change its structure, ultimately pivoting the location and logistics over 2 decades just to preserve its identity.
It's a fascinating case study in creating intentional, high-stakes logistical chaos for a genuine charitable cause. It's an adventure that promises discomfort, failure, frustration, and occasionally serious danger. And yet, thousands of people sign up for this guaranteed struggle.
The appeal is in the challenge.
The appeal is in the absolute, unmediated challenge.
Okay, let's unpack this. Before we dive into the rules, we have to recognize the DNA of this event. It's organized by a group known as the Adventurists, and their philosophy is everything here. It's the antithesis of a professional race.
Completely. In fact, they state a critical distinction right up front. Racing on highways is illegal. This is an unsupported journey designed purely for the experience and the charitable fundraising.
That distinction is paramount, isn't it? Mainstream rallies are all about speed and technical precision.
And they often rely on vast, dedicated support crews and sophisticated logistics. The Mongol Rally is a competition of sheer survival and self-reliance. It's governed by 3 cardinal rules, each designed not to help you succeed, but to maximize the likelihood of a glorious instructional failure.
And what truly sets this rally apart is its origin story. It didn't begin as a corporate venture or some meticulously planned charity event. It began as an act of, well, artistic, academic absurdity.
That's a crucial insight that frames the entire event's ethos. The rally was conceived back in 2001 by co-founder Tom Morgan, who was reportedly staring at his extremely disheveled Fiat 126.
Fiat 126, right.
And the thought process was essentially, what is the most ridiculous, impractical journey we could possibly attempt in this vehicle? The answer was Mongolia, cited as being 10,000 miles away as the drunk crow flies, boasting a fine selection of the world's worst roads.
So the first attempt actually failed. They ran into visa trouble, I believe.
It did. But the idea of intentional failure was so compelling that the formal creation of the rally, this grand concept of logistical chaos, was later displayed as part of Tom Morgan's BA degree show in sculpture at the Winchester School of Art in 2003.
It's an art project about struggle, framed as an adventure.
Which perfectly explains why the rules are so counterintuitive. They exist to manufacture the challenge, not streamline the process. So let's start with the first and most famous hurdle, rule number 1, the engine limit, or what participants affectionately call the small car mandate.
The core restriction is simple but insane. Vehicles should ideally be under 1,000 cubic centimeters with a strict hard limit of 1,200 cc.
The absurdity of this limit is where the real deep dive begins. When you consider the terrain, the journey includes the Pamir Mountains, the high plateaus of Central Asia,
The Gobi Desert.
the vast Gobi Desert, and thousands of kilometers of unpaved, corrugated, and often washed-out roads, using a 1,000 cc engine is a mechanical death sentence. These engines are designed for short trips, low speeds, and, controlled urban environments.
Right. We're talking about vehicles that typically have front-wheel drive, very limited ground clearance, and cooling systems designed for European traffic jams, not for climbing mountain passes in 40-degree heat. What are the specific technical risks that this small displacement mandate imposes on the teams?
Well, primarily you are looking at catastrophic overheating. Small engines under constant high-stress loads like sustained driving through deep sand or up a long mountain incline will struggle significantly.
Yeah.
Their small radiators and limited oil capacity mean heat dissipation is just poor. Secondly, the suspension systems on these lightweight city cars like the classic Fiat Panda or Daihatsu Charade are utterly inadequate. They're built with simple torsion bars or basic coil springs, not heavy-duty components. The constant vibration and impact from corrugated dirt roads, a standard feature in Mongolia, will quickly degrade suspension bushings, snap springs, and blow shock absorbers, often within the first week.
So it's not just the engine that's failing. The car is disintegrating around you due to inadequate components being pushed far beyond their design specifications. And this is by design, right? They want you to break down.
Absolutely. The adventurists actively want you to be driving a vehicle that is destined to break down, because that forces you into interaction. When your fan belt snaps in rural Tajikistan, You don't call AAA. You rely on local ingenuity, the mechanic in the nearest village, or your own completely improvised repair skills. This is the core mechanic of the adventure, forced engagement with the local people along the route.
And it forces people into finding these incredible, tiny machines that become famous in their own right. Beyond the Fiat Panda, we've seen truly antique entrants, such as the Akoda S110 used in the 2006 rally by the Akoda Power Turbo Racing team. These cars were already decades old and mechanically fragile when they set off.
Oh, the old Dakota S110s, with their rear-engine, rear-wheel drive layout, perfectly embody the original spirit when the rules were even stricter and allowed for any age of car, just under 1,000 cc. It's a deliberate, almost artistic handicap. And this mandate extends beyond four wheels. Motorcycles and scooters are also allowed, but they must be limited to 125 cc. A 125 cc scooter, that is a machine built for quick hops across town, maybe commuting 20 kilometers a day. Riding that across Iran, the vast Kazakh steppes, or negotiating the altitude changes of the Pamirs is a commitment to profound physical discomfort and vulnerability. It raises the stakes significantly. If the small car is fragile, the small motorcycle is downright exposed. If you're riding a tiny 125cc bike, you are fully exposed to the elements, the lack of road quality, and the sheer logistical difficulty of carrying spare parts, fuel, and supplies for weeks on end. It speaks to the philosophy. The greater the difficulty, the greater the story. If you complete the rally in a massive modern 4x4, you haven't truly engaged with the ethos.
Which brings us directly to rule number 2. Unsupported teams. This is the rule that transforms mechanical incompetence into genuine, high-stakes danger. The organizers are explicit. They wash their hands of your survival, logistically speaking.
Precisely. Teams are entirely self-reliant. The adventurers provide no support team, no dedicated rescue services, and no arrangements for accommodation, maintenance, or critically consistent access to guaranteed high-quality fuel. For you, the participant, this means that for 3 to 4 weeks, you are your own primary safety net.
The implication is stark. If your car breaks down in a remote region of Turkmenistan, you are responsible for everything. Fixing it, retrieving it, or finding a legal way to deal with its final demise. The sources confirm that this leads to constant mechanical failures, but also increased vulnerability to robberies and minor injuries because teams are operating entirely outside a supported structure.
Yeah, and we often see iconic images of this improvisation. Think of the photograph from the 2010 rally of an old ambulance, itself a rally participant, having to drag its own broken-down carcass out of a rutted track using a bizarre, improvised tow system. That improvisation, that reliance on your wits and the kindness of strangers is the very currency of the event.
And beyond mechanical failure, you are relying on your team, usually 2 to 4 people, to navigate the immense bureaucratic landscape. You're managing visas for sometimes a dozen or more countries, dealing with complex border crossings, understanding local laws, and securing lodging every single night. That alone is a full-time, high-stress job for a month.
It's an invitation to risk, but it's an invitation tied to a higher purpose, which leads us to rule number 3, the charity requirement. This is the necessary philanthropic mandate that elevates the chaos beyond mere recklessness.
Right. The mission is that every team must raise a minimum amount for charity, with the initial minimum set at £500.
And this is where the financial deep dive becomes crucial, particularly how the structure had to professionalize as the rally grew. In the very first rally in 2004, there was no entry fee charged by the organizers. It reflected its pure academic charity roots. But teams had to raise that £500 minimum, initially benefiting the charity, Send a Cow.
But rapid growth necessitated a shift in the financial model pretty quickly.
It did, dramatically. By 2006, the required minimum per team had doubled to £1,000, benefiting multiple established charities, including Send a Cow, Mercy Corps, and Save the Children. And the charitable impact was immediate and substantial. In 2006 alone, the rally raised over £200,000.
Wow. However, the formalization of the event introduced new fees. If we look at the structure since 2009, the adventurers charge a non-refundable entry fee of £650. This fee reflects the transition of the event to a private, profit-making entity, the League of Adventurists International Ltd., which was established to handle the rapidly scaling logistical and legal needs of the event.
That's a critical distinction. The money paid to the League covers the infrastructure required to make the chaos possible, coordinating launch parties, managing international paperwork, providing initial suggested routes, and maintaining the online presence. But the minimum charitable donation remains fixed at £1,000 per vehicle.
So, before you even buy your tiny, fragile car, fuel, or spare parts, You're making a financial commitment of over 1,650 pounds to the event and its associated charities. But you mentioned a further financial safeguard.
That is the 500-pound refundable vehicle deposit. This is a brilliant piece of logistical engineering designed to uphold an essential principle: preventing environmental chaos. The organizers learned quickly that if you drive an old banger 10,000 miles, the easiest thing to do is dump it on the side of the road when it finally dies. This deposit acts as a stick. You lose that 500 pounds if the vehicle is abandoned anywhere en route or at the finish line.
That deposit requirement directly foreshadows the massive logistical battle that the adventurists would face against international bureaucracy, forcing them to fundamentally alter the finish line and their entire operating model.
It's the ultimate irony, isn't it? An event dedicated to chaos had to become incredibly organized and legally nimble just to survive.
Here's where it gets really interesting. Focusing on this battle between chaos and constraint. The purity of the rally's initial concept, driving any old car to Mongolia, was instantly challenged by its overwhelming popularity and the immovable structures of international law.
The growth curve was explosive, forcing immediate professionalization. The inaugural rally in 2004 saw only 6 teams start, with 4 finishing. That's manageable chaos. But by 2005, the number swelled to 43 teams. Just 12 months later in 2006, 167 cars set off, with 117 making it all the way to Ulaanbaatar.
That is massive exponential growth, and it completely changed the dynamics of the organization.
It peaked in 2007. That year, the rally limited participation to 200 teams, setting off from London's Hyde Park. But the registration process demonstrated the fever pitch of its popularity. The first 100 registration spots were allocated in a staggering 22 seconds.
22 seconds. To claim a spot in a rally guaranteed to involve mechanical failure, heat stroke, and geopolitical headaches, that speed speaks volumes about the craving for authentic, high-risk adventure in the modern world.
It does. The remaining spots had to be awarded by ballot, demonstrating that the demand far outstripped the logistical capacity. This uncontrollable growth is the precise reason why the event transitioned from a pure, small-scale charity operation between 2004 and 2006 to being organized by the private, profit-making company, the League of Adventurists International Ltd., incorporated at the end of 2006. They needed a robust, funded entity to manage the logistics of hundreds of people crossing dozens of borders.
So popularity professionalized the financing, but international law professionalized the vehicles. This brings us to the biggest logistical conflict in the rally's history: the vehicle age versus Mongolian law conundrum.
This conundrum dictated the rally's structure for almost a decade. The organizers wanted old, small, cheap, failing cars. The Mongolian government, however, started implementing strict import restrictions that constantly threw the rally's core mandate into jeopardy.
Why were these restrictions put in place? Was it simply bureaucratic obstruction, or were there genuine policy drivers behind it?
It was primarily driven by legitimate policy concerns, specifically environmental protection and traffic safety. Mongolia, like many developing nations, sought to modernize its vehicle fleet and reduce urban air pollution. Allowing thousands of extremely old, high-emission, often poorly maintained European vehicles to flood the market, even for charity, ran counter to these goals.
So walk us through how these escalating restrictions forced the rally to compromise its own rules.
Initially, the rules demanded cars under 1,000 cc with no age limit. Those were the glorious days of the ancient death traps. But in 2009, the first major import restriction hit. Vehicles entering Mongolia had to be less than 10 years old.
And this immediately killed the availability of the charmingly old sub-1,000cc cars.
Exactly. Finding a car both under 1,000 cc and less than 10 years old that could be bought cheaply enough to justify the trip was nearly impossible. So the adventurists had to raise the engine limit to 1,200 cc. This accommodated slightly newer, often slightly more robust European models, but it significantly diminished the absurdity quotient. It was the first major compromise of the rally's spirit, forced by external policy.
And then the situation escalated further.
In 2013, the restrictions tightened even more dramatically. Vehicles entering Mongolia had to be less than 5 years old. A sub-5-year-old vehicle is, by any standard, a modern, relatively expensive car. It entirely defeated the purpose of driving a rickety, cheap car destined for glorious instructional failure.
A sub-5-year-old car is prohibitively expensive for a charity rally team. You're talking thousands of pounds lost or given away. And realistically, it should be able to complete the journey without exploding, which is what the spirit of the rally demands.
It was unsustainable, both financially for the participants and philosophically for the organizers. This led to what the adventurers termed the 2014 devolution. They realized They could not sustain the identity of the rally under the current import rules. They made the necessary U-turn. The rules reverted back to the original chaotic concept, 1,000cc limit, any age allowed.
But that required a massive compromise on the destination.
Precisely. To retain the small, old, cheap car mandate, the rally had to find a legal mechanism to prevent the vehicles from being permanently imported into Mongolia. The solution was the geographical shift. The finish line was moved from Ulaanbaatar, Mongolia, across the border to Ulan-Ude, Russia.
Let's detail the logistics of that move because the original finish line system was a key component of the rally's charitable contribution to Mongolia.
Right. Pre-2014, the cards were crucial assets. Through special negotiated agreements, initially via standard nonprofit tax exemptions on older vehicles, and later a bespoke agreement with the Mongolian government, the cars were imported duty-free. Once the rally was over, they were either donated or auctioned off for charity within Mongolia.
So the rally was providing a constant stream of cheap, functional vehicles to organizations and individuals in Mongolia where labor costs were low enough to make repairing and running older cars economical. The adventurous even placed contractual obligations on participants to ensure the cars were useful.
They did. For example, in the 2006 contract, there was a stipulation that teams should not remove essential utilitarian components, such as the rear seats. This was to ensure the vehicles retained their utility and fetched a reasonable price at auction for the local recipients. The charity wasn't just the cash raised, it was the tangible asset of the vehicle itself.
But the shift to the any age 1,000cc rule in 2014 meant that this donation mechanism, coupled with the tax exemptions, was no longer viable for Mongolia. So the cars could no longer stay.
Correct. Post-2014, when the finish line moved to Russia, the teams had to plan for the vehicle's ultimate disposition. Cars are either shipped back to Europe, an expensive and complex process, or driven back by the participants to be collected or scrapped there. This is why the 500-pound refundable deposit became such a strict enforcement tool.
It's the penalty for littering across Central Asia.
Exactly. If you dump your vehicle, you forfeit the deposit. Although it is a known cultural footnote that many vehicles that are abandoned outside the official finish line are quickly scooped up by enterprising local mechanics in Central Asia. They repair them and put them to use. So the spirit of repurposing often remains, even if the formal, centralized donation structure to Mongolia had to change. The logistical headache shifted from dealing with Mongolian customs to managing the retrieval or export of hundreds of vehicles from Russia.
We've covered the absurd rules and the geopolitical battles to maintain those rules. Now let's talk about the 10,000-mile stretch between the start line in Europe and the finish line in Ulan-Ude. The Mongol Rally is generally completed in about 3 to 4 weeks, covering a minimum of 13,000 kilometers. But the idea of a single defined route is fundamentally misleading. The organizers provide suggestions, but teams are entirely free to choose their own path, which often involves incredibly difficult and genuinely dangerous terrain.
That flexibility is central to the challenge. While most participants converge in a massive launch party, historically often in Prague, after teams have set off from the UK or other major European cities like those in France, Italy, or Spain, the actual route eastward is a strategic choice made entirely by the team. They're charting thousands of kilometers on their own.
And this choice is driven by a complex calculation of geopolitics, road quality, and scenery. Teams typically converge on certain hubs before scattering again across Central Asia.
That's right. Initial routes often head towards major European or Turkish hubs like Moscow, Kiev, or Istanbul. But the real strategic decisions start when they hit the Caucasus or Turkey. Teams choosing the northern route often stick to the relative, and I use that term loosely, stability of Russia and Kazakhstan.
But the southern route is where the legendary Silk Road convergence points and the high-stakes bureaucracy really come into play.
Indeed. Teams opting for the southern path, going through Turkey, negotiating countries like Iran, Turkmenistan, or Uzbekistan, often meet up at historic cities like Samarkand. This route is geographically magnificent, tracing ancient trading paths, but it is bureaucratically exhausting and technically punishing.
Let's elaborate on the geopolitical challenge of the southern route. Crossing a country like Turkmenistan, for instance, is not a simple matter of driving through and stopping for gas.
No, it's an immense hurdle. Turkmenistan requires transit visas, which can be notoriously difficult to obtain and often only grant a limited number of days to traverse the entire country. If your small, unreliable car breaks down, or if you encounter significant delays at a border crossing, you risk violating your visa and potentially being detained. This tight, non-negotiable timeline is a huge source of stress and risk. Similarly, the routes through Iran, while offering stunning scenery and hospitality, require meticulous planning, especially regarding fuel, as not all credit or debit cards are usable, and navigation can be complex.
The geographical range is astonishing. We've seen participants go as far north as the Arctic Circle, trying to cross Siberia, and as far south as Iran, Turkmenistan, and in some particularly ambitious and risky attempts, teams have skirted close to or entered Afghanistan.
That search for the most challenging, most exotic, and occasionally most dangerous path has resulted in some extraordinary achievements. The current record for the most countries passed through on the Mongol Rally is 41, achieved by an Australian team in 2018. Imagine coordinating visas, currency, and mechanical survival across 41 national borders in just 3 to 4 weeks in a tiny car. It's phenomenal, but that pursuit of extremity carries a heavy cost.
Which brings us to the unavoidable element of risk. The unsupported nature of the rally is not a quirk. It is a genuine documented hazard, and we have to talk about the high stakes involved.
What's fascinating here is the almost brutal honesty with which the organizers address the risks. The adventurous website explicitly and repeatedly warns participants of the inherent dangers. They're very clear. None of the available routes are comfortable, safe, or easily navigable, especially in the mandated vehicles.
We've touched on the common hazards: mechanical failures, opportunistic robberies, and minor injuries that come from intense high-speed driving on poor surfaces. But as the rally grew, the number of serious incidents, particularly high-speed car accidents due to fatigue, poor road conditions, and unfamiliar traffic rules, increased significantly.
This is the harsh reality of the event's success. Participants have required hospital treatment in multiple countries over the years, and we must acknowledge the specific tragedy that occurred in 2010, which underlined the high stakes of this challenge. A British participant died, and a teammate was seriously hurt after a road accident in Iran, near the border with Turkmenistan.
That incident serves as a sobering reminder that this is not a controlled environment. You are dealing with long stretches of intense driving, often on minimal sleep, in vehicles with poor safety ratings, on roads where local driving standards and infrastructure maintenance are far below what participants are used to in Europe or North America.
The organizers embrace this risk philosophically, arguing it is integral to the authentic experience. You have to genuinely fear failure or injury for the adventure to be real. But the consequences are very real, and the unsupported rule means that immediate professional emergency services are often hours, if not days, away, depending on where you break down.
Despite the inherent danger, or perhaps because of the compelling nature of that danger, the rally gained significant visibility, attracting media and celebrity participation early on.
The rally developed a cultural footprint almost immediately. Back in 2006, TV crews were accompanying some teams, and the event secured sponsorship from travel companies like Travel and Expedia, with those funds helping to offset the organizing costs, particularly the initial logistical coordination at the start and finish lines.
And some high-profile participants really raised the rally's mainstream profile.
The classic example is the celebrity entrant from 2007, Jack Osborne, son of Ozzy and Sharon. He participated with Amaryllis Night, and fitting perfectly within the small car mandate, they drove a 1991 750cc Fiat Panda. Their entire journey was documented and aired as a dedicated television show, Jack Osborne, Mongol Rally. That exposure was invaluable in boosting registration numbers and public awareness globally.
But perhaps the most widely recognized cultural moment wasn't a celebrity show, but pure viral content that captured that sense of unexpected connection that happens on the road.
That would be Joe Sabia's video from the 2009 rally, Tupac in Kazakhstan. Sabia managed to film dozens of random local Kazakhs singing lines from the classic Tupac Shakur song Changes, capturing a beautiful, unexpected cultural mashup. The video went viral, hitting over 1 million views by 2013, encapsulating that moment of genuine, unmediated cultural exchange that can only happen when you are forced by the failure of your tiny car to interact deeply with the community you encounter in the middle of nowhere.
That blend, the absurd vehicle, the extreme geography, the high risk, the bureaucratic nightmare, and the moments of genuine, moving cultural exchange is what makes the rally such a compelling, ridiculous, and ultimately successful concept. So let's bring this deep dive together for you. The Mongol Rally is a genuine success story founded upon a trio of counterintuitive pillars: the arbitrary, self-imposed vehicle restriction that guarantees mechanical failure, the unsupported travel mandate that forces total self-reliance and significant risk, and the mandatory charity fundraising component, which gives this intentional chaos a crucial moral purpose.
It is an adventure that had to constantly pivot and adapt. We have seen how its own explosive popularity forced it to professionalize and become a for-profit entity simply to manage the logistics of hundreds of participants, and how the legal requirements of an external government, Mongolia's push for newer, less polluting vehicles, forced the organizers to compromise their initial rules, only to revert them and move the entire finish line across the border to Ulan-Ude, Russia, just to preserve the core philosophy of driving a cheap, old, tiny car.
The fact that they were willing to move the endpoint thousands of kilometers, abandoning a fruitful donation system in the process, highlights how central the concept of the small car mandate is to their identity. The destination is less important than the struggle of the vehicle itself.
And that struggle traces directly back to the rally's strange beginnings, an act of pure academic curiosity by co-founder Tom Morgan, staring at his disheveled Fiat 126 and deciding the only sensible action was to drive it 10,000 miles to the world's worst roads. The genesis of this global, high-risk charity event was literally an exhibit in a Sculpture BA degree show. It is an art project about struggle and mobility executed on a continental scale.
That is the perfect encapsulation of the Mongol Rally's profoundly illogical but deeply human DNA.
If we connect this to the bigger picture, the Mongol Rally is arguably the ultimate exercise in intentional impracticality. Given the explicit official warnings of high risk, the known incidents of serious accidents, and the documented logistical nightmare of complex visa and vehicle restrictions, we have to seriously ask ourselves, why do people willingly sign up for an adventure defined by guaranteed discomfort and mandatory failure potential, knowing the organizers explicitly guarantee zero arrangements for safety or support? What fundamental human craving for authentic struggle, and what essential knowledge about mechanical repair, improvisation, and cultural connection is gained only by traveling the world in a vehicle designed specifically to break down, rather than one designed to succeed? It suggests that true modern adventure is found not in conquering the world with the best tools, but in accepting its inherent chaos with the worst.